Merhaba herkese, hoş geldiniz. Sesimi alabiliyorsunuzdur umarım. Ben Sude, kendimi tanıtayım bir kısacası. BİAS Mühendislik bünyesinde satış ve uygulama mühendisi olarak görev alıyorum. Müşterilerimize satış öncesi ve satış sonrası teknik destek sağlıyor. İhtiyaçlarına uygun çözümler geliştiriyorum. Deneysel akış ölçüm teknikleri üzerine çalışıyorum. PIV de bunun bir kısmını kapsıyor açıkçası. Öncelikle webinarımıza katıldığınız için teşekkür ederim. Bugün aramızda hem akademiden hem de endüstriden farklı kurumları temsilen katılımcıların bulunmasından açıkçası çokça memnuniyet duyuyoruz. Teşekkür ederim tekrardan. Bugünkü webinarımızın konuşmacısı Dantek Dynamics'ten Bölge Satış Müdürümüz Muhammed Hüseyin'i. Kendisi PIV ve lazer tabanlı ölçüm sistemleri konusunda uzun yıllara dayanan deneyime sahip ve birçok farklı uygulamada da aktif olarak yer almıştır. Açıkçası bu webinar Türkiye'deki katılımcılar için özel olarak düzenlenmiştir. O yüzden öncelikle sizlere ve sonra tabii ki de sizin huzurunuzda Muhammed'e teşekkür etmek isterim. PIV alanında bu kadar deneyimli bir uzman ile birlikteyken açıkçası soru cevap bölümünü aktif şekilde değerlendirmenizi ve merak ettiğiniz tüm soruyu sormanızı özellikle rica ediyorum. Şöyle bir katılımcılarımıza bakalım. Evet, başlayabiliriz bence artık. Now I would like to switch to English for the rest of the session. Muhammed, welcome again. It's a great to have you with us today. I hope you are doing well. We can see you right now. And our participants continue to increase. If you want, we can start before more time passes. We are looking forward to your presentation.
All right. Thank you, everyone, for joining us. It's quite pleasant to see we have this many participants, and very, very glad to share what we have to share with you and tell you a bit about what is new and what can be done with our system. So I will start sharing a presentation with you guys. Presentation contain a lot of videos. Sometimes because of your internet connection, it might appear with delay or you saw slow motion of it. So we have to work with this technology limitation we have now. But I hope you will benefit from it. So the base idea is to here introduce Dantek as a company, which I assume most of you are familiar, just for the people who are new, and also mainly focus on a particular image velocimetry known as PIV to just reintroduce it again and just show by today's technology what can be done in this area. So as a company, we are a Danish company based in Skålunde in Denmark. So we are kind of oldest company in this sector, selling scientific solution to university and some industries. We are established in 1947, and also majority of our product is export basis. We are a company of 120 plus people, highly educated, a lot of from academic background. So, and we are the company who introduced a lot of this product for first time into the market. We have 5 other offices in US, UK, France, Germany, and Japan as well. But we have wide distribution setup. So we more or less have a distributor in all major countries. And the country we don't have distributor still will be handled. So we kind of globally covering all this area. So our Dantec business is two sections. We have measurement of liquid and gas, which is fluid mechanics section, and then we have solid section, which is usually optimization material and component. So today we fall in the fluid mechanics section, which focus mainly on the PIV systems. To start, I will try to introduce briefly a PIV. Basically, PIV is a system with a major component contain camera, laser, or other source of illumination, synchronizer, and software. So obviously, illumination source, which is mainly laser, and then can be other sources, is to allow the particle in your flow have a good light signal towards camera, and the camera capture the signal as a photo, and then synchronization allow that good communication between laser, camera, and software. And then at the end, after capturing image, we do the processing. So this is the typical example of simple PIV system with single camera. We can see this kind of see-through pump. Basically, this particle will illuminate it through the light source. As I said, could be laser or other light sources. And then camera capture this as a photo, and which is here converted to a movie. And later software can convert this to velocity vector, as we can see here. So the concept basically works with the correlation of integration video within these images and displacement of the particle to generate one vector per integration window. So typically, this is the PIV can contain one camera or contain two camera. Basically, the difference will be you can measure third dimension velocity vector within a plane. Of course, you can add more camera, and instead of illumination in a plane, you can illuminate volume, and then do the volumetric measurement, which can be done by 3, but we usually recommend at least 4 camera. So example of such a measurement could be like this. This is like air pressure within a water tank. So we'll allow the movement of this move through the seeding particle, and you can see the illumination and the particle. And then these are like example of camera arrangement. They can look at that experimental section from different angle, and the result will be something like this. This is like particle tracking from the measurement. So you can measure 3D velocity or particle tracking through such a measurement. Before we start, we want to briefly talk about Dantec. Why Dantec? I mean, Dantec is one of the major players in this area. We've been in this business longest. We've been quite innovative in many areas. And then come to the PIV, usually the hardware is something all suppliers have access to it. So the one thing differentiate us from others is how we use this hardware and how to make best of it by having very advanced software feature. So this is we can offer as advanced feature. We have patented volumetric calibration refinement, which helps you with the stereo and volumetric measurement to increase to improve like reconstruction of particle, which is very important for this type of measurement. We have fully adaptive PIV. So I will make an example later on in an upcoming slide. basically, there is a lot of adaptive PIV out there, but ours is literally use particle density to adapt and works a bit more smart in that sense, that adapt much depend of what type of flow you're having. We have linear square matching algorithm. Some of you must be familiar. We have this product quad for while. It still is unique, and it can tackle more complex flow. We have flex grid, adaptive correlation. Again, it is another adaptive processing that helps you to extract more information. We will show that with example. We have dynamic masking and wall windowing. This wall windowing is become very key feature when you want to have very precise data very close to the wall. And then we have phase boundary detection when you work with two-phase flow, and then you want to separate this phase and study them separately. We have pressure measurement from our PIV, multimode decomposition technique. This is usually very helpful when you have very noisy measurement and data, and they want to use these techniques kind of to filter out the noise and have a better understanding also how flow structure works, what is the coherent structure in your flow, and more. We have multiple PIV uncertainty method. Uncertainty method is very important. We try to use all existing methods, combine them together. So basically you get a better understanding of your mechanism. We have very advanced synchronization with a very high resolution, very diverse and flexible. We do assemble particle tracking velocimetry, which is kind of enhanced particle tracking velocimetry by looking at history of your data. And then we have two interpolation, which is helps your data convert them to more realistic and what it actually should be. On top of that, to provide you with this, just few examples of advanced feature we have plenty more, but we try to focus on the one is more unique. We have very user-friendly. This is based on feedback we get from our customer, especially the one who had possibility to access from other system. So we have one of most easy operate system out there. For few clicks, you always can reach the destination of your analysis or acquisition. We add a lot of feature to make your job easier. I think these are become more important when you actually start doing your measurement. Things like imaging setup assistant, it practically help you sit behind your computer, do all evaluation where camera should be located, what angle is best, what light sheet you have, what is the thickness, distancing, and other parameter. Will you be able to get your field of view or not? So you can pre-arrange your setup already in software before you actually start going to your lab. So have a good understanding where you put your camera, laser, and so on, and what you will get out of it. We have some camera focusing assistant would help you for the application that you have difficulty to do that. We have automated multiple measurement, makes your job easier instead of like constantly, resetting your system for different locations. So it will do it for you in connection with the traversing system. We have distributed analyze. You can use all the PCs in your organization through the network to speed up the processing. We have active target, which is very makes your job much easier, especially in the area. Getting good calibration image is very difficult with low light or camera cannot get due to high reflection or highlight. So this target can work from a very bright room to very dark room. And in connection with that, you can do a lot of auto calibration, auto image stitching. We have a lot of live feedback from your measurement when you do, which is for some application become very crucial, especially application you don't have access to your camera and laser during measurement, and you want to sure actually you collecting right data, especially some application like submersible or combustion that's very expensive to operate those systems. This become very important. We have particle image simulator. If you wanna play with software, or a student want to do not having always access to the PIV system itself. We work with a lot of software, third-party software, so Python, OpenFOAM, MATLAB. So this can become very handy. Live target mark detection, live focus metric, and exploring exposure information, and then take device optimization storage for people who collecting a lot of data and struggling with the storage. And we also have very compatible light sheet optics, work with all laser beam, beam shape, and beam diameter, which can be quite advantage to make best of your laser, especially if you have low light budget. So these are the advantage. We will see some of this in actual example, how it works and what role they play. To overall give you a focus is we look at publication. We've seen since 2020 to 2025, based off Google Scholar Index, we see a lot of publication in aerodynamic turbulent flow. Second group is energy and combustion system, and microfluid as a third, biomedical and biological flow, force, and the hydraulic and environmental and geophysics, and industrial manufacturing process. So it's still a lot of focus on aerodynamic and turbulent flow. Traditionally, PIV introduced for that area and slowly moved to other areas as well. So as a top group, we still seen a lot of publication. Almost 30% of all publication is in this area. It, as I said, it's been like a core of domain for PIV, and a lot of CFD, LES, and DNS, a lot of numerical validation happening in this area, which is they use PIV, and is the biggest community as well, including a lot of wind tunnel. So the subcategory they're using this system most is our aircraft aerodynamics, automotive, jet and wake, supersonic, boundary layer turbulence, and volumetric for coherent structure. Here, like example of like wind tunnel with actual size car. You can see in this for PIV, the scale is this can get very big, up to the meter or more, and then you can do the measurement. This is an example of like wake flow behind the vehicle. And for this example, when you come to big wind tunnel, the seeding, you don't have much control of very proper seeding. This is like an example of a fog generator seeding. And usually you can see the seeding can be like varied in the density in different area of measurement. And also you will have different turbulent scale and flow. So here you can see adaptive PIV based on seeding density, also flex grid correlation can play very important role. These are the features we offer, and then help you to not only adjust your integration value based off the density, but also based off the flow behavior. For example, the area you have high density, you need a smaller integration video to generate vector. With the low density, you need a bigger. And this will help you to extract more valuable information. The second area considered very, very popular is energy and combustion-based application. Of course, gas turbines play a big role. Swirling flow beam has been there for quite a decade now, been very popular. Hydrogen combustion recently become more and more popular. Spray and optimization flow as well. Flame flow interaction, combined PIV PIF generally increasing, and also nickel-thermal hydraulic and wind turbine wakes. So other energy source as well. It's become quite popular more and more, and is getting a strong growth since 2020 due to hydrogen and sustainable fuel research, and also more researchers combining PIV with other diagnostic measurement they have. This is example of a flame you can see, and we're doing the PIV measurement. As you can see, flame is in the blue color is very visible. You have your fuel, you have flame, and then you have flame interface and flame front. So measurement of PIV for such things can be very challenging, but it is possible. This is example of such a measurement. Basically, when you do measurement, seeding density significantly different between the fuel area and combustion area. So, but having like a method like phase boundary detection and dynamic masking can help a lot, because phase boundary detection can detect the flame front here and also make them two zone, placed with flame and without flame. So, and then you can post-process them even separately and then merge the data later. So you can see for such a complex measurement, these features are key role. Other example is optical engine. We've seen a lot of optical engine through the time. It has been there for a while, but it's still very strong. So is this like any regular engine? But it can be optically be accessible while inside. This is an example of PIV data while this optical engine is performing. You can see the particle movement of the pistol, and this is the example of result you can get. So you can see you can have very precise PIV measurement. Again, kind of since you're having moving pistol, dynamic masking is quite important, and valve windowing is quite important. The way the valve windowing does adjust the integration window of PIV closer to the wall, so you can extract more valuable information near the wall. The next area is microfluidic and lab on chip. This area also quite fast growing. I would say the fastest growing areas due to a lot of biomedical diagnosis. They find how valuable could be PIV. And we've seen a lot of lab on chip technology, basically a lot of things getting macro scale. So a lot of company producing full functioning devices in a micro scale that can, have a flow movement and pump and everything is carved in a small chip. And also due to a lot of them can benefit from simple chip PIV setup with a single camera and LED based illumination. So micro PIV in micro channel still is a top in that area. Mixing efficiency in micro mixer. Also, a lot of electronic and multi-phase microflows we see. Heat transfer in micro devices also, and droplet and microfluid. So here we show another example measurement done with Antec system. This is our micro scale. You can see the drops were seeded with the particle. And then again, we can use our dynamic masking, adaptive PIV, to be able to extract a very precise PIV and velocity vector within these drops. Other microchannel example could be something like this. Again, this is again a wall windowing here is play many good role to make sure you can capture all the data. Still, adaptive PIV also could be very important due to fact you have very high gradient of velocity. So, and the outcome results become like this very clean information of flow within these micro channels. Biomedical and biological flow are also are quite hot topic. We've seen a lot of cardiovascular flow, a lot of like heart valves and ureters. Respiratory airflow also become very important, especially after COVID. Respiratory airflow is basically breathing organism, and blood analog flow also. This been there for a while. Fish swimming and insect flight from environmental perspective also quite hot subject. Cell scale flow also as well. We've seen a lot of strong post-COVID growth in respiratory and airflow studies and non-intrusive diagnostic like PIV. This will give a very valuable information how breathing and airflow within a room or within a group of people. But the example we choose here is this one. This little bug called Acartia tonsa. This is you can find them in the ocean, especially in the coastal side on every sea. This is ecologically and ecosystem-wise is very important. So there have been a lot of study on this bug behavior and other mechanism where the customer were interested to see the movement and flow pattern around it. So again, it is possible to do such a measurement. As you can see here, you can do very precise PIV measurement around this to see how flow move while this bug move. And this is due to fact of dynamic masking. And here we did target stabilization. Basically, we target the moving object. And when you do that, then you will be able to do other statistical analysis as well, averaging, creating modes, POD, and other parameter, which is also very valuable. And this is, you can see in this smaller scale and this complex movement, you still can get very precise data thanks to the dynamic masking, which provide that possibility. So this dynamic masking works very good for any movement and moving object within your flow while you want to do PIV measurement around that. Another example could be movement of this fish within a tank. So this also shows another example how good this dynamic masking can perform. So you can have very precise measurement of your velocity, vorticity, and other parameter you require to extract from such a movement. So these are again this dynamic masking doesn't care about the shape of object, the movement, and anything else, and still can extract very precise information very close to your subject. The last area we will the last area we will study explain is hydraulic and environmental and geophysics. This is we see more and more the requirement for measurement and not only in towing tank, which has been there for a while, but in damp and intake vortices, open channel flow, river hydraulic, and even open sea, coastal and sediment transport and environmental mixing. So one of the few systems we saw last few years is to do PIV measurement to actual ship who's sailing in the sea. So basically they want to see how propeller performing while they're sailing in the sea. And we designed a PIV system, confined them with this kind of camera housing, as you can see. They're mounted just behind the propeller, and they can do PIV measurement at any time while the whole ship sailing within a sea. Here you can see the parking position, which we have our calibration target here, and illumination done through the body of the ship. We have example, we do illumination from outside the ship as well. And if you want to look at this camera housing, it will be something look like this. The camera is within it. All the cable go through this water seal tube. And then everything within camera can be controlled remotely, both lenses, focuses, even sharp look. And then you can do very precise measurements while you are in a ship. Related to the same subject, a lot of studying done in towing tank. Towing tank been there for quite a while, and the measurement usually done with this type of torpedo shape setup. Within this torpedo, you have your laser light and you have two cameras, and this torpedo shape move together with the towing tank to do the measurement while your subject or your experimental boat moving within the water. This is one is installed within water, and then this is while moving and doing the measurement. The example like this also shows the importance of having full remote control access to your PIV and other parameters that need to be adjusted. Also getting very live feedback from your particle density and focus and exposure information, because you don't want to do this measurement few times and later when you process it, you realize, oh, you didn't have enough seeding, or your focus was off, or other exposure parameter was not correct. So we are one of very few supplier will give you online access while you're doing sample measurement. You can already see if you're collecting very good data. So this is the advantage of user friendliness, and that can be for any other application which is access is not as easy. The last area we discussed here is industrial and manufacturing process areas. I mean, we've seen 5% publication in this area, but probably publication should be much more, because these are industrial customer. They usually not keen to publish much, but we have seen worldwide a lot of inquiring. The most areas we're seeing a lot of inquiry is mixing tank, flow structure interaction, reactors, cooling flow in electronics, air conditioning flow like work and process optimization. So here we have an example of how flow structure interaction setup could be look like. So we have here we have our normal flow jet. Here we have membranes that can deform while this kind of flow heated with this frequently produced wave flow hit the membranes and create a deformation. We have two sets of four camera here that do the PIV measurement, and we have two camera that do deformation. So this setup together can give you information about flow and also deformation of the membrane. So this both systems together communicated with same software and can be synchronized with same software, and data can be mapped on top of each other. So this is a video we made to show how this flow structure interaction would work. And then, as I said, this is your membranes and jet flow. So basically, jet flow shoot it with certain frequency, and the movement and the pressure will have an impact in membrane and create a deformation. And this is show velocity vector and pressure field and also impact on these membranes. So if I visualize it for you this way, so you will have a better clear visualization of it. You can see a stream line of PTV tracking from the particle. And also you see this tube, which is represent the pressure and the impact of the pressure on the membrane and the deformation. So basically, to be able to do that, we extract pressure from PIV data, which is very good feature we have. We also use some interpolation, which is basically by this kind of interpolation, you make your flow follow and comply with actual fluid mechanic and kind of continuity of the flow. And then that's also end result match the reality much better. And also we use assembled PTV. That means we're not just tracking between two frames. We look at history of development and assemble it together to have much better and more precise tracking. This was the example we have, and some of application is quite popular. And then you can see the possibility you have with the PIV and how much you can do. So of course you can do much more, but we try to keep our presentation fit in this time slot. So we just basically sample pick on some of this example from a customer who has our system and do this kind of a study to show what they do, what they can achieve, and what you can get inspiration for your study. Okay, thank you very much. Now we have a good remaining time for a question. If there is any, I hope you all enjoy it and get some sort of benefit from it.
Thank you so much, Mohammed, for the insightful and beneficial presentation. We will now move on to the question and answer session. If you have any questions, please feel free to write them in the chat, or I can turn the microphones of people who raise hands. We are waiting your questions. Okay.
Well, hello.
Hello.
My voice is
Yes.
coming correct?
Yes, yes.
Okay. Thank you, Sude and Mr. Mohammed. It was very enlightening. Thank you. I have a question about the cavitation and bubble formation in the, for example, take as a fluid when we are experiment. My name is Sefa, by the way. Sorry. I'm an academician. In academy, we are using, of course, PIV. And I would like to ask, when we are using in water channel, for example, adding some particles, as you mentioned, and agents. So I would like to, of course, to see them, but there were some cavitation forming in water channel, especially. Yeah. So how could we get into it?
When you have both bubble and particle present in your flow, of course, your illumination reflect light from both particle and bubble, and because the bubble usually is in bigger size, they ended up, creating a lot of noise. You will not be able to actually see the signal from particle. The most common way to tackle this kind of application is, first, best solution is to add fluorescent particle. This fluorescent particle, basically, when they absorb your light or laser light, they convert that to different wavelengths. And then you can put a filter in front of your camera and block the laser light and only accept the new wavelengths generated from this fluorescent particle. So this way you only see the particle, and doesn't matter if it's behind the bubble, front of the bubble, or around it. So this way you can do. It is more realistic for a closed loop because this particle both expensive and also cannot be drained in a city water. So it's designed for closed loop, that you reusing same water in a loop and doing PIV measurement. But if you have a bigger loop and it's not possible to see the whole water, you can also inject them with a different way close to your measurement section and in upstreams. So while the particle reach to your measurement section, you will have such a measurement. So using fluorescent particle to convert light to new wavelengths and putting camera filter to look at them without seeing the bubble is one of the most used techniques for this purpose.
Thank you very much. There was a second question,
Yes.
if you want. Okay. Maybe it's kind of funny, but I would like to ask anyway. Do you prefer to add milk into water to tracking the particles? It's actually a practical way. I research.
You mean liquid milk or powder milk?
Powder milk.
Powder, yeah. I think that's possible. Basically, the seeding, there is no limitation what could be the seeding. I think a relaxation factor of your particle is a decision maker. Relaxation factor means how fast your particle adjusts to the flow velocity change. So if you have a particle that can have adjust to the velocity change and turbulent change in your flow quick enough, that can be your particle. It could be milk powder, could be any other type of powder, or it could be like polymer as we give glass powder. It could be the choice could be yours as far as you know this particle follow your flow, because at the end we want this particle to represent actual flow, and the key factor is, will this particle do that? And if do that, and milk powder of course have a good reflection index, so you get very strong signal from it. But the downside is it can contaminate your measurement area in long term. This can settle eventually bottom of your channel. It can grow algae. So it has compared to plastic, which doesn't have plastic powder, doesn't have these problems. So it has its own downside. But if you have possibility to change your water frequently and clean the channel, that could be for you.
Thanks, sir.
Yeah.
Thank you so much, Sefa, for your questions. And we have one more question.
Mehdi?
Mehdi, yeah. I allow the microphone.
Do you have my voice?
Yes.
Can you
Yes,
hear?
Yeah.
First of all, thank you so much, Dr. Hosseini, for presentation. I have a couple of questions, but I will ask them, most of them, after the meeting through email. But one of the challenges that I face is the recording or the time that the camera takes the image, and then we try to record it to the PC. That time, it takes ages for some cases. Are there any plans in the future for the new software that we can also kind of decrease the time of the recording and then again recording to the PC, or in terms of like the live tracking of the data?
All right. First, I would like to see what type of camera do you have? Do you know the model?
Phantom V641.
Okay. This high-speed camera, of course, they need to have their onboard memory to collect data. Of course, transferring this data to the PC it can be very challenging. It's usually, you collect a lot of data in such short time and takes for a long time to transfer them. So it is limitation that exists through the hardware industry. Is not our limitation. As I explained, with the lower frame rate, low resolution, using frame grabber, other type of camera, you can monitor live phenomena while it's happening and even check if it's a good result or not. But and for a high-speed camera, it should be possible. Again, it depends on what type of PC and what type of hardware you have, because software has that possibility. But if at the moment, if your hardware has that limitation, will not allow you to do that, is the limitation your hardware has, and that's based of what is you have currently. But if your hardware allow you to get access to it, or give our software access to do that, there is such a feature. You can access your measurement while it's happening, and then of course to post-process it, of course you have to save them, and then it depends what type of PC or camera you have. The saving can take a few minutes or quite long time, and then after saves you do the final post-processing to extract all the data.
Thank you so much, sir. I will ask the other questions through email.
Yeah. All right. Thank you. Thank you.
And one more. Yeah, you
Yes.
can speak.
Hello. Hello, Murat. I think he's still mute.
Murat, can you hear us?
Yes.
Yeah.
Can you hear me now?
Yeah, we can hear
Hi.
you.
Hi,
Yes.
hello. I just want to ask, how do you measure pressure from the velocities, or do we also include that LIF system?
Pressure, you can measure it from velocity directly. But of course, when we measure the pressure, we simply use physics. Just picture Navier-Stokes equation. In Navier-Stokes equation, you have 4 major parameters. You have your velocity, you have your pressure, you have density and viscosity. So if we assume your density and viscosity is a constant during your measurement period and is not compressible flow, so basically we read the velocity, we put it in that equation when we extract the pressure. And of course, through the development of software, we measure it with a lot of pressure measure with other devices to compare and validate it. So now it's performing very, very nicely. So if you have a very clean experiment, PIV done correctly and data collected correctly, and we are assuming density and viscosity is constant during your measurement, preferably temperature and others as well. So you extract pressure this way. Yeah.
By the way, about the previous question,
Yes.
is it possible to change the bit rate in that camera that could speed things up, since PIV doesn't need more than 8 bits?
I think it should be possible. It's difficult to generalize it for all camera. If you send us the
Yes.
camera model you have, I will
No,
check it.
about the previous question, the camera asked previously.
Okay.
Maybe it can be a solution for them.
Yes, it could be. Yes.
Okay, thank you very much.
Yeah. Okay.
And does anyone have any other questions? Okay, no one. Thank you for all questions. I would like to thank Mohammed for presentation and for
Thank you,
taking the
everyone.
time to answer our questions. Thank you so much, really. And also thank you for all participants. We will continue to organize similar webinars based on your interest and learning needs. As a reminder, this webinar has been recorded and will be uploaded to YouTube. You can watch again and again if you want. And Mohammed, is there anything would you like to add?
I would like to also thank you all for participation. I wish I will meet all of you in person. I will travel to Turkey, and we can discuss in detail in future if we meet. Meanwhile, if you have any question, you can reach me through BIAS. Feel free to contact for advice, for any technical question. So we will be happy to reply to you and work with you. And basically, the goal is we learn from each other. So anything you share with us, we learn a bit and we share what we know. So looking forward to work with all you guys. And thank you for participating.
Yeah. And tüm herkese teşekkür ederiz katılımınız için. Dediğim gibi YouTube'dan tekrar izleyebilirsiniz. En yakın zamanda yükleyeceğiz YouTube kanalımıza. Bizi oradan da takip edebilirsiniz BİAS Mühendislik olarak. Bu şekilde kendinize iyi bakın. Teşekkür ederiz katıldığınız için webinarımıza.
Teşekkürler.
Thank you.